All right, let's dive right into one of the biggest questions there is. How did our universe begin? We're going to explore a really fascinating idea that challenges something we take for granted every single day, time itself. So, let's just start with a kind of mind-bending question. What if the past, present, and future weren't a straight line? What if it all just was? Now that might sound like something out of a sci-fi movie, right? But believe it or not, this idea is actually rooted in real physics, and it just might be the key to unlocking a massive cosmic mystery.
And this isn't just some wild guess. According to the laws of physics that we use every day, for a photon, a single particle of light, time and distance literally stop existing as it travels at light speed. From its point of view, a journey from one end of the universe to the other happens in zero time. It experiences no trip at all. Now you gotta hang on to that. Weird fact. We're gonna need it in just a minute.
Okay, so why are we talking about photons and timelessness? Well, it's because this truly strange concept might just solve a major puzzle about our early universe. Let's call it the temperature problem.
You see, when we look at the cosmic microwave background, which is basically the afterglow from the Big Bang, it's shockingly, almost perfectly, the same temperature everywhere we look. But here's the problem. The universe is gigantic. How could 2 points, billions of light years apart, have possibly settled on the exact same temperature if they never had time to exchange any heat? It's like finding 2 cups of coffee on opposite sides of the planet, both at precisely 80 degrees Celsius. You'd know something had to have connected them.
Now, the leading theory to solve this is something called cosmic inflation. The idea is that in the very first fraction of a second, the universe just ballooned outwards, expanding way faster than the speed of light. It took one tiny uniform hotspot and stretched it out to become everything we can see. The math works, for sure, but it does require some pretty extreme conditions. But what if there's another, maybe more elegant way to look at all this?
And this brings us to a brilliant analogy that really helps frame this new perspective. So for a second, just forget about the cosmos. Let's think about something much simpler.
Simple enough, right? You've got a car, a tunnel that's 1 mile long, and a constant speed of 60 miles per hour. From the driver's perspective, this trip is going to take exactly 1 minute. No surprises there at all.
But what if you were an observer, standing outside, watching this happen? You see the car go into the tunnel, and in the very same instant, you see it pop out the other side. You would have to conclude it traveled at some impossible, unbelievable speed. Meanwhile, the driver inside feels a perfectly normal 1-minute trip pass by. This is the core idea right here. 2 observers, 2 completely different but totally valid experiences of the exact same event.
So, who's right? The observer who saw an instantaneous jump, or the driver who experienced a whole minute? The radical idea here is that they both are. Their experience of time is asynchronous. It's relative to their own frame of reference.
Okay, let's connect this back to the universe. How does our car in a tunnel story help explain that uniform temperature problem we were talking about?
Let's go back to that photons world. In the very beginning, before matter even existed, the universe was just a sea of light. This wasn't a place with our familiar ticking clock. It was a fundamentally different kind of reality.
In this primordial quantum state, the linear, forward-marching time we all experience just hadn't been born yet. The rules were being governed by quantum mechanics, where particles can be in many places at once, and connections across vast distances can be, well, instantaneous.
So here's how this 2-clock history might have actually worked. Let's just walk through it. Step 1. The early photon-only universe starts to expand. Now, from its own perspective, that's the driver's clock, this was a slow, leisurely process. Which brings us to step 2. This expansion might have taken hours, maybe even days or longer, and that long duration is the absolute key to step 3. During this period, photons could become entangled. That's a wild quantum connection where 2 particles act as one, instantly linked, no matter how far apart they get. This allowed them to share information and even out the temperature across the entire expanding space. Then, step 4, everything changes. Matter finally forms. The moment it does, a brand new clock starts ticking. Our clock, observer time. And from our new perspective, as we see in step 5, that entire long, slow expansion looks like it happened in a fraction of a second. It's the car instantly exiting the tunnel.
You see, this reframes the entire debate. It's not about whether inflation was fast or slow, it's about whose clock you're using.
So, what does this all really mean? It means the theory of rapid inflation is totally correct, from our perspective. But the idea of a much slower, longer expansion is also correct from the early universe's perspective. Time itself is asynchronous. The two clocks are not in sync. And that seemingly impossible temperature uniformity, it's not a puzzle at all. It's simply the natural result of entangled photons having plenty of time to connect during that long, slow phase.
This means there's no contradiction. There's just a profound truth about the nature of time itself. Two completely different timelines, describing the exact same event, can both be true. It all just depends on your point of view.
And that really leaves us with a final, fascinating question. If something as fundamental as the passage of time is relative, if it depends on the observer, what other aspects of our reality are simply a matter of perspective?